Okay, hi everyone. So in this video, we're going to be solving a couple questions based on the preliminary chapter. So I just chose a couple questions based on those topics, and we'll go through it and see if we could solve it. So the first one is saying, let A be some non-empty subset of R, and the script F be the set of all real valued functions defined on A. So what's a real valued function? Well, it's just a function that maps from A into the real numbers. And we're going to define a relation, um, between these two functions to simply mean F is related to G if and only if there exists some finite set, let's call it EFG. And of course, it's finite, so it's a finite set of points. And this set is going to depend on the functions f and g, such that the function f, when restricted to the set A minus EFG. So what that set is saying, so what is this set A? So you could do slash like this, E, F, comma, G. This is just the set of all points, let's say y in A, such that y is not in this set. So all the set is saying is that you take the set A and you remove from it all these points, x1, x2, and so on, xm. So if it happens that the function f restricted to the set is equal to this function g restricted to the set, we say that these two functions are equivalent under this relation. But we have to show it's an equivalent relation. So we're asked to prove that this relation is an equivalent relation on this set. So we need to prove, so required to prove that this relation, so an equivalence relation means it satisfies. So let me just instead say we require to prove that this relation is reflexive, symmetric, and transitive. Okay, so let's try reflexive first. Okay, so reflexive. So reflexive basically means I need to show that every function f is related to itself, right? And notice that they said the set A is non-empty. Okay, so the set A is non-empty. So we could say since A is non-empty, that means I could take any, so take any, let's say, point of A, and I need to construct a set, this EF, comma, in this case, it'll be EF, comma, F. So take any element of A and consider the set. So I'm going to define the set EF to be simply the singleton E. Okay, so this set is clearly finite. Remember, that's the condition, that this set must be finite. Then, so clearly, if I take now the function f and I restrict it to the set A, which it's originally defined on A, and I remove from it the singleton point. Okay, so I'm just saying take any function f its domain is A, remove from it one point of A, and look at the function on that new set. So this function is obviously going to be equal to the same function, right? I didn't change anything. To the same function restricted to the same set. Okay, so thus f is related to itself. So reflexive is very easy. All we have to do is just construct a set where the function is equal to itself, and that could be any set. So that's reflexive. The next one is symmetric. Okay, so for symmetric, I need to suppose I have two functions, f and g, and f is related to g. So of course we know we need to show g is related to f, but if f is related to g, then that means then there exists. So straight from the definition, what does it mean for two functions to be related to each other under this particular relation? It means that there exists some finite set. Okay, and we call that set E, F comma G. And let's so it's a finite set of points. So let's put some points in it. Let's say they are just m points, such that if I look at the function f only on the set A and I remove from A these finite points, okay, so that's what this means, the restriction of a function to that set. Okay, so since f is related to g, it means that this function is equal to the function g restricted to the same set. Okay, but remember, equality, I could just flip these functions around. So that implies that restricted to the set is equal to f, right? I just switch the functions around because it's equality. Okay, and that's symmetric. So thus, what have we found? We have found a finite set E comma f g such that the function g, when restricted to this set A minus those points, is equal to the function f when restricted to that same set. So that means g is related to f. Okay, so that's symmetric. So symmetric is pretty straightforward. Now we want to do transitive. Okay, so transitive now is suppose f is related to g and g is related to another function, let's call it h. So from definition of this relation, what does that mean? It means that then there exists two finite sets. So finite sets, um, let's call one of them E, F comma G, that contains, let's say, points x1 up to xm, and another finite set, let's say E subscript G comma H, that also contains finitely many points, and let's call these points y's. So there's no reason why there must be m y points. So there are m x's. So let's say there are n y's. Okay. So what I'm saying is the number of points in E, F, G, there's no reason why that should be the same number of points in E, G, H. So in general, there are different number of points, but still finite. Okay, so what's so special about these sets? So there exist finite sets such that the function f, when restricted to its domain minus, so if you want, so we write minus of f. Okay. minus EFG is equal to the function G when restricted to the set A without EFG, and G when restricted to the set A without EGH is equal to the function H when restricted to the set A without EGH. So we're just removing from the set A the x's, and f and g are equal to each other on that new set. And we're removing from the set A the y points, and g and h are equal to each other on that set. So that's all the same. So what I need to do is come up with a new set, a finite set, such that f and h equal to each other on the domain without those points. Okay, so it's easy to see that if I just let E, F, H equal to the union of these two sets. Okay, so you just union it. F, G, E, G, H. Okay, so obviously this is a finite set. So this is a finite set such that. So what happens if I take now the function f and I remove from its domain all the points in E, F, H. So I remove from A all the x's, x1, x2, all the way up to xm, and y1, y2, all the way up to yn. So I remove all the x's and I remove all the y's. So if I remove all the x's and all the y's, then this function is equal to, so we know that f and g are equal to each other once I remove all the x's. Okay, so they will still be equal to each other even if I remove all the y's now. And I know that g and h are equal to each other once I remove all the y's, right? And I have removed all the x and all the y's. So g and h are equal to each other on this set. Okay, and that's what I want. I want f, I wanted to construct a finite set. In this case, the finite set is E, F, H, such that the function f is equal to h on the set of points A minus that set. Okay, so you could say f is related to h. Okay. So we've shown it's symmetric, reflexive, and transitive. So therefore, this relation is an equivalence relation. So that's that proof. Okay, so in this next question, goes as follows. So let f be some function from the set of natural numbers into R. If f is injective, we need to prove that the range, which is given by f of n, is a countable set. So proof. So I'm just going to call this set, right, the range. I'm just going to call this set A. Okay, so our target is if f is injective, I need to prove, so I'm just calling this guy here A. I need to prove that A is a countable set. So of course, we know that the range is contained in the codomain. So the domain is N and the codomain is R. So let the range be A. So we could say maybe then by the definition of the range, Okay, the range in this case is simply the set A. We know that the range has to sit inside the codomain. The codomain in this case is the set of real numbers. Now, note that if it happened that the range A was equal to the codomain, right? Then what happens if the range is equal to the codomain? Those functions are surjective functions. So if the range was equal to the codomain, then the function f would be surjective. Okay, then the function would be surjective. But we already know that the function is given to be injective. So therefore, it will be bijective. And hence, f will be a bijection between these two sets. F will be a bijection between the set of natural numbers and the real numbers. And that will imply, so if you have a bijective function between two sets, that means that they have the same cardinality. Okay, but we of course know that this is a contradiction. The cardinality of the natural numbers is a denumerable set, so it's countable, and the real numbers is uncountable. So this is a contradiction. The real numbers has a cardinality strictly bigger than the natural numbers, so which is a contradiction, right? So which is a contradiction. Okay, so that means that A cannot be equal to 1. Okay. So what we're going to do now is we're going to define a new function. Okay, so before, what did we assume? We assumed that if A is equal to R, A is the range of the function. So if the range of the function is equal to all of the real numbers, we get a contradiction. So that means that the range of this function, A, cannot be all of the real numbers. Okay, so let's see what happens now. So we could define a new function. Define a new function. And I'm going to call it g now. And this function g is going to be very similar to f. So this function g, like f, it's going from the set of natural numbers. But so you see f was going from n into all of the real numbers. G is going from n into the range of f, which is the set A. Okay, so I'm now creating a new function going from n into the range of f, which is A, and I'm going to define this by saying that g of n, so it takes in a natural number because it's defined on the set of natural numbers. So g of n is simply the same function as f. So g of n is equal to f of n for all natural numbers. In other words, what this function g is, right? So I'll just say here, in other words, all this function g is it is the function f with the codomain, codomain with the codomain restricted. Okay. So, well, the proof is basically done because what does that mean? What am I trying to show? I'm trying to show that the set A is countable. Okay. So now I have G is a link between N, the set of natural numbers, and the set A. So all I have to do now is show that if I could somehow show that G is bijective, that means that A will have the same cardinality as N. In other words, A will be countable. Um, so we could say plus G by construction. So I want to show G is bijective. By construction, notice that G is simply the function f, but I just shrink the codomain. So f was already injected. So G by construction is injective. Right? Since you could say since f was injective and G is simply f. Since f was injective, okay, and surjective, right? Why is G surjective? Because G is simply f. G is the function f. So G is just the function f mapping from the set of natural numbers into its range. So by construction, G will be surjective. So therefore, G is bijective, which implies that the cardinality of its domain is equal to the cardinality of its codomain. In this case, it's A. But what was A? A was f of n, the range of f. So the set is countable. Okay, so let me try to draw a picture to show what this function g is. So let me draw f first. So f is a function from n into r, right? But we're told that f is injective. Okay, we were told that f is injective. And we showed in the beginning of this proof that f cannot be surjective. Remember, because we showed that if a, which was the range of f, happened to be all of the real numbers, then we will get a contradiction. So f cannot be surjective. It cannot map into the entire real numbers. So let me draw the range of f. Okay, so this set here, proper subset now of R, this is the set A. Okay, which is simply the range of f. So what is the function g? The function g is just f, but instead of mapping into all of the real numbers, I'm just mapping into this smaller set. This is the function g. Okay, so therefore, by construction, so I take f, the codomain of f is too big. So what do? You just shrink it. You shrink the codomain down to the range of the function. So therefore, by construction, this new function that I'm calling g will be 1-to-1 because it's simply f was 1-to-1. And it will be onto because I constructed it to be onto, right? I mapped it directly into its range. Okay, so that was the, so that's a picture of exactly what was going on there. Okay, so in this next question, we have, suppose that f is some function from a to b, and a is uncountable and b is countable. I need to prove that there exists an element b such that it's pre-image. So again, this f to the -1 is not f inverse, it's the pre-image. So it's a pre-image of the set B is uncountable. So let me draw a picture of this. So here is the set A. Okay, and we're told that A is uncountable. Okay, so it always helps to draw a picture if it's possible. It's not always possible to draw a picture. And B, we are told is countable. And F is some mapping between them. Here's F. Okay. Now we want to prove that there exists an element B in the set B. Okay. I want to show that there exists some element B in this set such that its pre-image is uncountable. So what is the pre-image? The pre-image is everything in A that maps into B. Let me draw that circle. Actually, let me do a different color. Right. So this set here is the pre-image of B. What does that mean? That means when you apply F to this set, it maps all those elements to B. That's what the pre-image is. I'll write it up here. The pre-image, okay, let's just do a B, is the set of elements X belonging to the domain A such that when you apply F to that element, you end up in this set B. But since it's a singleton set, instead of saying f of x belongs to the singleton B, the better way would simply be f of x equals to B. Okay, so it's simply all of the points in the set A such that when you apply f to it, you get B. Okay, so that's the pre-image. What I want to show is that this green set is uncountable. Right, I want to show this guy here is uncountable. And we're given a hint to try a proof by contradiction. So let's see. Proof. And we put here by contradiction. Okay, so we could start up a proof by saying suppose A is uncountable and B is countable, right? It's a proof by contradiction. So what do I want to show? Maybe right here. So required to prove that this set, the pre-image of B, is uncountable. Okay, so that's what I need to prove. But it's a proof by contradiction. So I'm going to assume the negation of that. Okay, proof by contradiction means we're going to assume the negation of what we want to prove. So the negation of so required to prove, so it should be there exists an element in B. Maybe there exists an element B in B such that. So what is the negation of this green statement? The negation of there exists means every element in B is such that its pre-image is countable. So assume for every, so the negation of there exists is for all for every. Assume that for every element in B, the pre-image or its pre-image, okay, and that's given by f to the -1, its pre-image is, so I'm trying to show that this pre-image is uncountable. Proof by contradiction means I assume the negation. So its pre-image is a countable, okay, set. Okay, so that's a set up. So I now need to figure out some way to get a contradiction. The contradiction is not very difficult because essentially what we're saying now is that for any point in this set B, for any point, if I look at its pre-image, that is, if I look at, for example, this point, if I look at the set of points over here, such that when I apply f to it, I end up by this point in B, I'm assuming that all these sets are countable, okay? Now notice if I take the pre-image of every single point in B, B is the codomain. So if I look at the pre-image of every single point in the codomain, and I union all of that together, I should recover my entire domain. Because a function, what is a function? A function means that every single point in my domain is mapped to something, okay? It's mapped to something. So if I look at the pre-image of every single point in B, that pre-image is either going to be empty, either there are no elements in A that maps to it, or according to my assumption, it's going to be a countable set. So countable means, of course, the empty set is countable. Okay, so that observation right there is the contradiction, will lead us to a contradiction. So then we can write the domain A as, so I'm going to write the domain A as the union of all these pre-images. So I'm going to take the pre-image of every single element in B and union all of those together, and I'm arranging this over every single element in B. Okay, and by doing that, we could reconstruct the domain, right? So A, of course, is the domain, and B, of course, is the codomain. And by assumption, all of these sets are countable. Okay, by assumption, all of these sets are going to be countable. So what do I know about B? Remember, we assumed something about B. B is countable, right? We assume that B was countable. So this is a countable union of countable sets, which is countable. So hence, A is the countable union, okay, because the union ranges over every element in B, and we were told that B is countable. So hence A is the countable union of countable sets, which is countable. Okay, but what do I know about A? Of course, A was uncountable. So that is a contradiction. Okay, so that's the contradiction right there. Therefore, what did I assume to begin with? We assume this. This is the negation of what we want to prove. Okay, so that was wrong. So if this statement is wrong, it means that there exists an element in B such that the pre-image is actually uncountable, which is what we were asked to prove. Okay, so in this next question, we're going to now start looking at upper bounds and lower bounds, supremums and infimums. So let me just quickly recap what is what are these bounds and what's a supremum and an infimum. So recall. So all of this takes place in what is called an ordered field. An ordered field is just a field, so for us it'll be the field of real numbers with an order relation, and the order relation is just a relation that satisfies certain conditions. Effectively, it allows you to say when one element is less or smaller than or bigger than another element. So once you have an ordered field, you can start talking about upper bounds for a particular set. So, um, so recall, okay, so I don't want to use U and L, so maybe let's do alpha and beta. So alpha, which belongs to this field, is said to be an upper bound of some set A. Of course, A is contained in the field. If, so we recall in the definition, if it's an upper bound, it means that, let me write it in a different color. It means that all the elements in A must be less than or equal to this alpha. Okay, and this must hold for all elements in A. So upper bound simply means everything in A is smaller than it. And beta, which again belongs to the field, is said to be a lower bound of the set A if, so the condition for a lower bound is that every element in A is bigger than it. Okay, and notice that the alpha and the beta only needs to belong to the field. We are not saying that they must also belong to the set A. They may or may not belong to the set A. And in general, a set may have many upper bounds and many lower bounds. So for example, if we take as our set, so if we take as our field the real numbers, and as our set A, let's just say open, so the interval 0, 1, open at 0, and let's just say close at 1. Yeah, let me draw back the line. Right, so here is 0, here is 1. Then upper bounds are simply all the elements in the real numbers which are bigger than every element in A. So notice every element in A only goes up to 1. So on upper bound, all of these elements up here, any element bigger than 1 is an upper bound. Right, so all of these are upper bounds for A. In fact, 1 is also an upper bound for A because every element in A, x is between 0 and less than or equal to 1. So you could choose 1. 1 is the upper bound. So in general, there are many upper bounds for a particular set, and they may or may not belong to the set. In a similar way, where the lower bounds, so a lower bound is simply every element in the set is bigger than the lower bound. So all of the lower bounds, you will find them over here. So these are the lower bounds, okay? is 0 a lower bound? So is every element in A bigger than 0? And the answer is yes. So again, you could choose 0. But notice in this case, 0 will be a lower bound, but 0 does not belong to A. So when a set has a lower bound, so in general, not all sets have upper and lower bounds. Okay, so hopefully you remember all of this. If a set has an upper bound, we say that the set is bounded above. And if a set has a lower bound, we say that the set is bounded below. And if a set has both of them, we say that the set is simply bounded. Okay, so bounded means both above and below. Now, the idea of the supremum and the infimum comes in because when we want to do proofs, sometimes we want a particular upper bound, a particular lower bound, or maybe we want the best bound. So what is the tightest bound? So again, notice that of all these upper bounds, the tightest upper bound, or the smallest of them, or the least upper bound, will end up being 1. Because if I decrease 1 a little bit, I'm going to fall inside of the set, and I'll get an element that is bigger than it. So that brings the idea of what is known as the least upper bound, or the supremum. Okay, so the least upper bound, sometimes it's called LUB, or we simply say the supremum, or you could say SUP, or supremum of a set A is, so it's 2 is an upper bound such that, so in order for it to be the least upper bound, it must first be an upper bound. So it's an upper bound such that for any other upper bound, let's say U prime, or I didn't say what the supremum is, the least upper bound or supremum, let's call it U, supremum U, okay? U belonging to the field. Of a set A is an upper bound such that for any other upper bound U, so if this is the least upper bound, or the smallest of the upper bound, it means if I have any other upper bound, okay, U prime, this implies that U, the supremum, is the smallest of the upper bound, so U must be less than or equal to U prime. Okay, so if you take any other upper bound, that upper bound will be bigger than it. And in a similar way, we have the same thing for the lower bound. So what is the tightest lower bound? So all of these are lower bounds, but if we keep increasing the lower bounds until we hit 0, and notice that we cannot get a lower bound bigger than 0, because then there will be elements of A that actually is smaller than it. So we want the largest lower bound, or the greatest lower bound. So the greatest lower bound, sometimes called GLB, or the infimum. So we'll give it a letter L belonging to the field. And again, just like upper bounds, the supremum and the infimum may or may not belong to the set. Okay, sometimes it belongs to the set, sometimes it doesn't belong to the set. So the greatest lower bound or infimum of a set A is a lower bound such that for any other lower bound any other lower bound L prime, this means that so if this is the biggest of the lower bound, if I take any other lower bound, it must be less than or equal to this guy. Okay. Now, when we're doing proofs and we want to prove that something is the supremum or the infimum of a set, it doing it this way, we need to make like some sort of condition concrete that we will need to prove. So what I'm saying is that if you want to prove something is a supremum and prove it is the infimum, from this definition, it may not be that straightforward as to what is the procedure or what is the path that you will do it. So there are what are called characterization terms that are basically what is equivalent definition of the upper bound and the lower bound. So that's given over here. So we have two of them, characterization of supremum and characterization of infimum. It's just another way, another equivalent way of saying what the supremum is and what the infimum is. And this way, it gives us a very precise way to prove that something is the supremum and prove that something is the infimum. So we'll go through the proof for the supremum, and I encourage you to sit and write down the proof for the infimum case. The proof for the infimum case is pretty much the same as the proof for the supremum case. You just need to adjust the signs, the inequality signs accordingly. So I want to prove this characterization of supremum. And it says that, of course, let F be an ordered field and A non-empty subset of F. These two statements are equivalent. So U is the supremum. Another way of saying that is that U is an upper bound for A, and for any positive number epsilon, there exists, or I could find an element in A such that that element is bigger than U minus epsilon. In other words, if U is the supremum, U minus any little bit, U minus epsilon, is not an upper bound for A, for any epsilon. Okay, so it's an equivalent statement, which means I need to prove 1 implies 2 and 2 implies 1. Okay, so proof for the characterization of supremum. Okay, so we'll prove 1 implies 2 first. So that says if U is the supremum, I need to show that U is an upper bound, and for any epsilon, U minus epsilon is not an upper bound. So suppose U is the supremum of some set A, then, okay, well, what was the definition I gave you? So over here, I said that the supremum of a set A is an upper bound, right? Such that this condition holds. So by definition, if I say U is the supremum, it's automatically a upper bound. So suppose U is the supremum of A, then we could say by definition of the supremum, U is also an upper bound for A. So U is an upper bound for A. So that follows from the definition, because the definition of supremum is it's an upper bound such that certain condition holds. So now the part where we have to do a little bit of work, which is for any epsilon. So we could say let epsilon be bigger than 0. Then I want to show that u minus epsilon is not an upper bound for the set. So notice that the u minus epsilon is of course less than u. Okay, but so so this is the proof right here, because I said that u is an upper bound for E. Okay, so if u minus epsilon is less than an upper bound, it means that u minus epsilon is not an upper bound, or cannot be. Let me write that to stress. That is not. So u minus epsilon cannot be an upper bound for A, okay, because it's less than u and u is upper bound. So if u minus epsilon is not an upper bound for A, that means that there's some element of A which is bigger than it. Because if there's no element of A bigger than u minus epsilon, then u minus epsilon would have been an upper bound. But I'm saying it cannot be an upper bound. So that means there exists some element of A, so let me say some x belonging to A, such that this element is bigger than it, okay? Because u minus epsilon, whatever that is, it's not an upper bound. So there's some element of A that's bigger than, right? And I believe this is what we wanted to prove, right? Yeah, right? So that's what we wanted to prove. So that's the proof for 1 implies 2. So now we need to prove 2 implies 1. Okay. So now we need to prove 2 implies 1. So I could say conversely, suppose that u is an upper bound for A, and so I'm assuming condition 2 is true. Condition 2 was this thing with epsilon. So I'm assuming that u is an upper bound for A, and for any epsilon bigger than 0, I could find that there exists an element in A such that that element will be bigger than u minus this guy, epsilon. What do I want to prove? I want to prove now u is the supremum. Okay, so I'll do a proof by contradiction. I'm going to assume that u is not the supremum. Assume that u is not the supremum of this set A. Okay, if u is not the supremum, then there exists another, the supremum is the smallest upper bound. So if u is not the supremum, that means there exists another upper bound. Let's call him u prime of A such that, so if u wasn't the smallest upper bound, there's another upper bound u prime that is smaller than u, because u is not the smallest of the upper bounds. Okay, so u prime is strictly smaller than u, right? So this means I could convert this less than into an equality, okay? By saying that u prime, right? U prime is equal to u minus something. Call him epsilon or epsilon prime. Okay. How do I get this? So let's just put some numbers to it. Let's just say u prime was 5, right? And let's say u was 7. Then we could say 5 equals 7 minus some amount, right? Of course, the amount will be 2 in this case. So that's what I'm saying. We could convert this less than sign into an equality sign by subtracting some small amount from u. Okay. So therefore u prime is equal to u minus epsilon prime for some epsilon prime. For some epsilon prime bigger than 0. Okay. Now by assumption, I know that, so by assumption, remember what did I assume? I assumed that for any epsilon, I could find an element in A such that x is bigger than u minus epsilon. So by assumption, there exists some element in A, let's call him x prime, such that that element is bigger than u minus epsilon prime, right? So what I'm doing there is I'm invoking this part. For any epsilon, I could find an element in A such that x is bigger than u minus epsilon. So I'm taking a specific epsilon, which is epsilon prime. And for that particular epsilon prime, there exists a particular element of A, x prime, such that x prime is bigger than u minus epsilon prime. But what is u minus epsilon prime? This is equal to u prime. Okay, so I got x prime is bigger than u prime, but u prime was an upper bound. So this is a contradiction. Okay, this is a contradiction because u prime is an upper bound and I'm getting an element that is bigger than an upper bound. Okay, so therefore, I assumed something that was wrong. What did I assume? I assumed u is not the supremum. So therefore, u was actually the supremum. Okay. Okay, so that's the proof for the characterization of supremum. And like I said, the characterization of the infimum is very similar to this. The idea of the proof is pretty much the same idea. You just have to adjust the less than sign to greater than sign. Okay, so now that we proved the characterization of supremum, we're going to apply it to prove some additional results involving supremums. So one of them is how the supremum works when we take the two sets and add them together essentially. So for example, if A and B are non-empty subsets of R that are bounded above with supremum A and supremum B, then I want to prove that this new set S given by A plus B. So essentially what you're doing is you're taking every element in A and adding it on to every element in B. And you're forming this new set. So I want to prove two things. This set S is bounded above, so that's the first thing. And not only is it bounded above, the supremum of this set is simply the supremum of A plus the supremum of B. In other words, you can so in other words, if we were to denote the set S by the symbol A plus B, right? So this is just a symbol to denote what this set S is. Then in other words, what this is saying is that the supremum, if A and B are bounded above with supremum, this is saying that the supremum of A plus B is equal to the supremum of A plus the supremum of B. So in other words, the supremum behaves nicely. And okay, so Let's see how to prove this, and we will make use in this the characterization of supremum that we just proved. So proof. So the first part is I want to show that this set S is bounded above. So let's take any element in S. So suppose I take some element S in the set S. Then if I have an element from this set, it means that this element can be written in the form A plus B, right? For some A belonging to the set A and some B belonging to the set B. But that implies, remember, S, which is equal to A plus B. A is an element of the set A. So A is less than or equal to its supremum, and B is less than or equal to its supremum, because the supremums are upper bounds. So think of these supremums as simply numbers. The supremums are upper bounds. So every element in A will be less than its supremum, and every element in B will be less than or equal to its supremum. So therefore S, which is the sum of these two numbers, will be less than or equal to the supremum A plus the supremum B. Okay, so all I did was so this inequality and this inequality, add them together. Add them together and you will get this part here. Okay, so let me just neaten this up. All right, so what did this show? This shows that S is bounded above, right? Because, so think of supremum A and supremum B as simply numbers. So supremum A plus supremum B, that's just a number. So what we showed is that any element of the set S is less than or equal to this fixed number. Okay, so this means that this number, supremum A plus supremum B, whatever it is an upper bound. Okay, that's the definition of an upper bound. Every element of the set S is less than or equal to this number. So if a set has an upper bound, it's bounded above. So hence, S is bounded above. So now we've showed it's bounded above. Now I need to show that it has a supremum that is equal to this number, right? So since this number, the supremum A plus supremum B, and again, think of this as a single number, since this number is an upper bound for S, so maybe let me say it this way, since the supremum of S, since the supremum of the set S is the least upper bound, or the smallest upper bound, is the least upper bound of S, and this number, supremum A plus supremum B, is an upper bound, then what do we have? So which one is the smaller one? Then the supremum of S is the smallest of all these upper bounds. So the supremum of S should be smaller than or less than or equal to this number, supremum A plus supremum B. Right? So we call this guy maybe equation 1 or something. So I want to prove the supremum S is equal to supremum A plus supremum B. What have we showed? We've showed half of it. We've showed that the supremum of S is less than or equal to the supremum of A plus B. So now we need to show it's bigger than or equal. Okay, so we've shown half of it already. To show the other inequality, we need to invoke the characterization of supremum. So I could say, let epsilon be bigger than 0 by the characterization of supremum, right? That tells me that there exists some element in the set S, right? Oh, then let's do A and B first. Because supremum A is the supremum of the set A and supremum B is the supremum of the set B. Okay, so for any epsilon, that means that there exists an element in A and there exists an element in B for the same epsilon such that this element A will be bigger than this supremum of A minus that amount, epsilon, and same thing for B. This element B will be bigger than the supremum of B minus that epsilon. Okay, and to neaten things up in the end, because essentially what I'm going to do is add these two inequalities. Of course, you know the trick. You do epsilon over 2 and epsilon over 2, so you get a nice and neat epsilon in the end, right? But that's just to make things neat. Okay, so now I just add these two. I just add these two inequalities, and I get A plus B, that's the left-hand side, is bigger than supremum A plus supremum B minus epsilon, right? And now let me just rewrite this. So I'm just rearranging the inequality. So I'm going to write it like this. The supremum A plus the supremum of B minus epsilon is less than A plus B. And I know A plus B must be less than or equal to its supremum, right? Because this, of course, is an element in S. So every element in S is less than or equal to its supremum. Okay. So this means that the supremum of A plus the supremum of B is, so take epsilon over, is less than the supremum S plus epsilon. And since epsilon is arbitrary, right? So this holds for all epsilon. So you can see since epsilon is arbitrary, or since this holds for all epsilon, we have that the supremum of A plus the supremum of B is strictly less than, or sorry, less than or equal to the supremum of S. Okay, and this I call 2. So from 1 and 2, combine them both and you get what we need. So from 1 and 2, this means that the supremum of S equals supremum A plus supremum B. Okay, so that's what I want to show. Okay, so now we want to look at if I have two sets, A and B, and these sets are bounded subsets of R, and A happens to be a subset of B, what is the relationship between their supremum and the infimum? So it turns out that we're going to prove it in this one, that for any set, any non-empty set, the infimum of that set is always less than or equal to its supremum. Okay, and that's something that should make a lot of sense because the infimum is a lower bound and the supremum is an upper bound. So it makes sense that the infimum will always be less than or equal to its supremum. But in this case, we have some set B and A is contained in it. Okay, so this one is saying that so again, the infimum of A should be less than or equal to its supremum. But they're saying since A is inside of B, then we have the infimum of B will be less than or equal to the infimum of A and its supremum, and the supremum of B will be bigger than or equal to these two. So in other words, when A is contained in B, the infimum and the supremum of A, you could think of this are bounded by the infimum of B and the supremum of B. Okay, so you get this nice inequality relationship between the infimum and the supremum of these sets. So let's try to prove this. And the proof of this is straightforward once you understand the definition of the supremum and the infimum, because actually all we need for this proof is just the definition. Okay, so proof. So, well, we didn't mention it before, but the reason why we even have supremums and infimums for, so since it didn't say anything about the supremum and the infimum existing, all we are told is that A and B are non-empty bounded subsets of R, then maybe we should write a statement saying why it is that the supremum and the infimum even exist. So suppose A is some subset of B, and both A and B are non-empty and bounded. Subsets of R. So the real numbers have this nice property called the completeness property that says that every non-empty bounded subset has a supremum and an infimum. So by sometimes called the LUB property or the GLB property or the completeness axiom. So by the completeness property, right? It's actually why the real numbers are so important in analysis. So by the completeness property of the real numbers, the supremum and the infimum of A and B exist. Yeah. So now, so I know that these numbers, supremum A, supremum B, infimum A, infimum B, whatever these numbers are, they exist. So first, let me say if I let X be an element of A, then of course we know that X will lie between its lower bound and upper bound, but the infimum of A is the lower bound. And the supremum of A is the upper bound. So in other words, of course, X will lie in between these two. Okay. And this holds for all X, right? So this holds for all X. So since this holds for all X in A, right? This means that the infimum of A is always less than or equal to its supremum of B. Okay, so that's something that should have made sense. So what we've showed there is this inner inequality, that the infimum is always less than or equal to the supremum of that set. Now we need to show that the infimum of B is actually less than the infimum of A. So we could say now, let X belong to B. Okay, and again, we have the same thing, that the infimum of B is less than or equal to this X, which is less than or equal to the supremum of B. Okay. And notice that okay, so let me, Yeah, so I want to use x belonging to A. So it's the same x. So sorry about that. It's the same x I want to use. So let x belong to A, then that means that the infimum of A is less than or equal to the supremum of A. So what I should have said here is since now so we assume that A is the subset of B. Yeah, that's better. Now since A is the subset of B, then X belongs to B. Yeah, so that's extremely better. So because since we let X belong to A is a subset of B, so maybe I could include it in this diagram. So over here is X. X belongs to A, which means X belongs to B. Okay, so if X belongs to B, now we know that X will obviously lie between the infimum of B and the supremum of B. Okay. But where did X originally come from? X originally came from A. So since this holds again for all X in A, it follows. So this is saying that the infimum of B is less than or equal to all X in A. In other words, the infimum of B must be a lower bound for A. So it follows that the infimum of B is a lower bound for A. Is a lower bound for A, and also since the supremum of B is bigger than or equal to every element in A, this means that the supremum of B must be an upper bound for A. So, upper bound for A. Okay. Now, by definition of the supremums and the infimums, remember the infimum is the greatest of the lower bound and the supremum is the smallest of the upper bound. Okay, so what we just showed. So let's take this part first. The infimum of B is a lower bound for A. Okay. So this implies, but the infimum of A is the largest of all the lower bounds that A has. Now the infimum of B, what I have underlined in red, the infimum of B is a lower bound for A, which means that the infimum of B is less than or equal to the infimum of A. Okay, so if it's a bit confusing, maybe let the infimum of B be equal to maybe beta or something. So then you could say beta is a lower bound for A, and we know that all lower bounds for A is less than or equal than the infimum. So beta will be less than or equal to the infimum of A. But beta in this case is the infimum of B. Okay, so we get that part of the inequality. And of course, the infimum of a set is always less than or equal to the supremum of that same set. And the supremum of B, if you want you to call this alpha, is an upper bound for A. So if I have an upper bound for A, that upper bound should always be bigger than the supremum of A, right? Alpha is an upper bound for A, so the supremum of A should always be smaller than alpha because the supremum of A is the smallest of those upper bounds. But what was alpha? Alpha was the supremum of B. Okay, so this last inequality just follows, so this chain of inequalities actually just follows from applying the definition of the supremums and the infimums, right? So that's what we wanted. Okay, so in this next question, we're going to look at um, how functions behave when we apply them to the union or the intersection of families of set and how their pre-image behave. So suppose that we have two non-empty families of sets, AIs and BIs. Now, these are indexed by some index set I, and this index set may be countable or uncountable, doesn't matter. And the AIs are all subsets of A, and the BIs are all subsets of B. And we have a function f mapping from A to B. So let's try to draw a picture of this. So here's A, here's B, f, some function between them. And well, I can't draw infinitely many, so I'll just draw a few of them. So the AIs are, let's just say, sets in here. Okay, and they may overlap, maybe they don't overlap, maybe they are finite, maybe they are uncountably many, doesn't matter. So these are the AIs. And the BIs are subsets of Bs. Right, so again, they may overlap, they may not overlap, doesn't matter. These are the BIs. So the proof of the unions and the intersections are pretty much the same idea. So I will do the ones for unions, and I will leave it up to you to write the proofs for the one for intersection. Notice that for the second one, you just have subset over here. Okay, so in general, this one is not equal. This is not equal, which means that you could find a counterexample where the intersection over some subset f of AI will not be a subset, of f of the intersection of AI. Okay, so try to find some sets where this wouldn't work. Of course, all you need all you need to show this is you don't need infinitely many sets. So maybe just take two sets, A1 and A2, or something like that. That'll probably be easier. So just find two sets, A1 and A2, such that the intersection, such that f of A1 intersect f of A2 will not be a subset of f of A1 intersection A2. Right? So try to find. And you will, of course, need to give the function as well. So that will show that you cannot get equality for this particular one. Okay, so, but for the pre-images, F inverse, they are better behaved and you do get equality if you look at the pre-image. Now again, F to the minus one is not F inverse, it's the pre-image. It's the things from A that map onto these sets. Okay, so let's look at the proof of the first one. So the first one, so there are a couple of ways you could do this. The most straightforward way is how to show, for example, how to show two sets are equal, X and Y. That's the same thing as saying X is subset of Y and Y is subset of X. So that's what I'm going to do. So required to prove F union of the AIs, so union over I, is a subset of union over the I's of F of AI and the reverse one now. And the union over the I's of F of AI is a subset of F union I AI. Now, there are many ways to do these proofs. In fact, if you probably look it up in textbook, maybe they might do it in maybe 2 lines or something like that. Because there's very efficient ways of proving this. I think for some of these proofs, you might actually be able to prove both at the same time. So using these equivalent statements in the entire proof, so you don't have to prove X is subset of Y and then go prove Y is subset of X. Maybe I'm pretty sure you could find proofs where they prove both are equivalent at the same time. But since we're going through these proofs not to be efficient, but to understand how these functions work over unions and how preimages works over our unions and intersections, I'll break it up into two pieces, right? So the proof of the first part is, I could say, let. So I'm going to prove this guy first. So f of the union of the AI, so if I'm taking an element of this set, notice, is a subset of B. F of union AI, this set lives in B, okay, because F takes things from A and moves it to B. So this set lives in B. So I'm going to let Y belong to this set. Okay, so what I'm saying is this set is a subset of B. Okay. So maybe put a Y here. Right, so that's Y is over there. So Y belongs to this set. Then, so if Y belongs to this set and F is a function, it means that there is an element in A. Right? There's an element in A, let's call it X, that mapped on to this Y. Right? So then, there may be more than one, because I don't know if F is injective or not, but then there exists at least one, some X belonging to the set union of the AIs, such that when I apply f of X, when I apply f to X, that is equal to Y, I of course land up in this set. Okay, so far I've just used the definition that f is a function. So if I have f of, so if I have a value Y in the set, then there must be something that maps onto it. Why must there be something that maps onto it? Because they say that so they say that these sets are non-empty. Yeah, so there must be something that maps onto it. Of course, if this set is empty, then the proof is finished because I simply have the empty set on both sides. Okay, so let Y be some element in F of the union of AI, then there must be some X in the unions of the AI, such that when I apply F to that X, I end up in this set. So now, since X is in the union of AIs, then X must belong to AI for some I. Okay, so for some I in here. And F of X belongs to the image of this set, right? If X belongs to AI, then F of X belongs to the image of this entire set. Remember, this thing is what we call the image. The image is just you take all of the points in AI and you throw them into the set, into the function F, and f of ai is whatever comes out of that function. Hence, f of x must belong to f of ai. But f of ai, f of ai, of course, is a subset of the union of all f of ai, right? Because any set is a subset of the union of that set with other sets. So this guy is a subset of the union. And what was f of x? F of x was y, right? F of x is y. So y belongs to the union. So what did we do? We took a y belonging in this set, and we showed that y must belong to this set. In other words, f of the union of ai is a subset of the union of f of ai. Right? So that's the first inclusion I wanted to show. Now we need to show the second inclusion. So the second inclusion, again, we let so f of ai belongs in B. So again, let y belongs to f of, right? Let y belong to the union of f of ai. Okay, and of course this is in B. So since y belongs to a union, then y must belong to one of them, f of ai for some I. Okay, and I'm essentially writing the proof I have above, but backwards, because these statements were going back and forth. So then y belongs to f of ai for some I. So if y belongs to the image of this set, and there exists some x in ai, and of course ai is contained in A, such that when f was applied to this x, it ended up in f of ai. So this is just the definition again of the image. If y is in the image of ai, then that means there's some x in ai such that when you apply f to it, you land up in f of ai. Okay? And f, so now notice that f of ai is a subset of f of the unions of ai, right? Because ai is one of the set in this union. That is, what is f of x? Y. So that means y belongs to f of this union. Which means, again, what did we show there? We took a y in the union of f of ai, and we showed that that y belonged to f of the union ai. So this means that the union f of ai is contained in f union ai. So we showed both of them. This one, this one. Okay, so now let's show number 3, which is f inverse the union of bi is equal to the union of f inverse bi. So it's like the same thing, but so again, I shouldn't say inverse, but it's a pre-image. It's the same thing, but for the pre-image. Okay, so now for the third one. So the third one was in um, required to prove. Now it's the pre-image of the union of the BIs is equal to the union of the I's. Okay. So again, I need to show that the left-hand side is subset of the right-hand side and the right-hand side is subset of the left-hand side. Notice that these these sets live in E. These sets are subsets of E. That's where the pre-image lives. Right? So if here's A, if here's B, let's say this set here is the union of BIs. Here's F. This set here is the pre-image of the union of the BIs. Okay, that's what the pre-image is. It's everything such that when you apply F to it, you land up in this set. So the pre-image lives in E. So I could say let X belong to the set F inverse union I of the BIs. Okay, so if X is in this pre-image, then by definition, when I apply F to X, this element will belong to the union of the BIs. Okay, so this element here, that's X. So when I apply F to X, it's going to stand it inside of this set, which is a union of the BIs. Now, if Fx belongs to the union of the BIs, so now if you want to, you can let f of x equal y or something, but we don't need to. If f of x belongs to this union, so that implies, hence, f of x belongs to BI for some I, for one of those I. Okay, so if f of x belongs to BI, this implies that x belongs to the pre-image of the set BI, right? Because if f of x belongs to BI, then if I look at everything that maps onto BI, x will be in there. That's what the pre-image of BI is, everything that maps onto it. So x belongs to f inverse BI, and of course, f inverse BI is a subset of the union of f inverse BI, because that's one of the sets in this union. Okay, so therefore we have that. So we started with x belonging to f inverse union BI, and we showed that x belongs to union f inverse BI. So therefore, f inverse union BI is a subset of the union f inverse BI. Okay, so now we need to show the next direction. So conversely, let x belongs to the union of f inverse BI. Now, if x belongs to the union, then x must be in one of them. So x must be in one of them for some I. And if x belongs to the pre-image of BI, then that means when I apply f to x, I land up in BI. Right? That's what this means. It means when you apply f to x, this element is in BI. Okay, so hence f of x is in Bi. And now Bi is clearly a subset of the union of the Bi's. Okay. So therefore, if f of x is belongs to the union of the Bi, then that means x must be in the pre-image of the union of them. Okay, and yeah, so that's it. That's the last line. So we're done there. So therefore, what do we show? We took an x in the union of f inverse Bi's, and we showed that x is in f inverse the unions. So therefore, the union of f inverse Bi's is a subset of f inverse the unions of the Bi's. Right, so usually these proofs sound this long, but I just went through every single step, so it's a bit clear. So again, let me just make a diagram there. So again, what you need to keep in your mind when you're doing these things is that if here is A and this guy is B and F does something like this, then if this is a set AI, right? If you take all the elements in AI and you throw them and you apply F to this set, it takes it to a subset of B, and this subset is what we call the image of AI. And we write it as F of AI, right? So that's the image of the set AI. It's the set of points that you get when you apply F to every element in AI. Now, what is the pre-image? The pre-image, so notice for this one, I drew AI first. The pre-image, slightly different. Draw a new diagram for this one. So once you have a good intuition about how the image and the pre-image of these functions work, doing that proof is not too difficult. So the pre-image means I start with a set in the codomain B. I'm just trying to figure out what to call it. Oh, Bi, yeah, Bi. So the pre-image of Bi is everything in A such that when you apply F to it, it takes you over here. So this is F inverse Bi, right? So it's two different views of looking at things. You could either take a subset of the domain and look at what you get when you apply F to it, that's the image, or you could take a subset of the codomain B, and you could look at what are all of the elements in the domain that got mapped here. So again, this is called the pre-image. So one is the image, one is the pre-image of Bi. And by just applying the definition of these things, you could prove these statements. So there were two more for you to try. That is proofs involving the intersection, which again is very similar to the union, except that if an element is in the intersection, it means it's in all of them.